So this is the first periodic trend we're going to cover. And it is the size, okay, how much space does an atom take up? Okay, now this is a radius, you know, if you think of a radius of a circle, it's half the distance. Typically that's how it's measured. Atoms are very, very small, okay, but it's based off of about how much space does the electron cloud take up? Because remember, the nucleus is very, very small compared to the electron cloud, which makes up about 99% of the volume of an atom. So the size of an atom has everything to do with where those electrons are, what energy level, and then how they're being pulled by the nuclear charge, the effective nuclear charge in the nucleus. How many protons are there? So here is a great image, okay, trying to show the relative size of atoms as you go either down the periodic table, wrong one. As you go down the periodic table, I hope that you see that the size is getting bigger. If we look at hydrogen versus lithium versus sodium, potassium, rubidium, cesium, francium, the size is getting bigger, okay? And if you look at these numbers, that's the size of the atom in a unit called picometers, okay? So remember, picometer is 10 to the negative 12. Very, very, very small. Okay, so atoms are very, very small. So just so you know what those numbers mean. All right, so if you look at this image, hopefully visually you can see as you go down, the size is getting bigger. We're going to talk about why here in a second if you can't deduce it yourself. All right, and then as we go across, if you look across the periodic table, if you look from lithium to neon, which is what I was talking about, that second period, okay, lithium is the biggest and neon is the smallest. Okay, and if you look at sodium to argon, the third period, it decreases as you go from left to right. So let's talk about why that is. Okay, why are the trends the way they are? So as you go down the periodic table, you're adding electrons to new energy levels. Those electrons are getting further and further away. So you would expect the size to get bigger. That one should be a no-brainer, okay? Electrons are being added to new energy levels. The distance is further away. It's going to be bigger. However, as we go across the periodic table, atoms get smaller. So why is that? Remember, you are adding more stuff to the atom. So maybe you'd think, okay, as I go across, it would get bigger. Okay, but remember, you're adding more protons, you're adding more electrons, and you're adding more neutrons. But remember that as you go across the period, the distance from the nucleus doesn't change. Like electrons are being added to the same physical space. And so as you go across the periodic table, those electrons are being added to the same, about the same distance. So then you have to look at what else is changing. However, remember, as you go across, the number of protons is also increasing. Remember, from lithium to neon. And so the nuclear charge increases. Well, what happens when you have more protons in the nucleus, but electrons are being added to the same physical space? Well, protons are going to pull tighter. That Coulombic attraction is going to be greater. And so the atoms are going to be smaller. They're going to feel a greater pull, a greater attractive force, those electrons, and so they're going to want to be closer to the nucleus. They're going to want to be held in tighter. So the distance gets smaller. And I think I have another little image down here. So this is like showing down a group, you know, electrons being added to different energy levels, so further away. But this image is trying to show that you have more protons in the nucleus. Electrons are attracted to it. Remember that Pogel activity that we did. The more protons there are sitting in the nucleus, the more attracted those electrons are, and so they're going to be pulled tighter. So if we go back up here, as you go across, the size is going to get smaller because you're adding electrons the same distance. However, you're adding more protons from left to right. More protons are going to cause those electrons that are also being added to be pulled in smaller, or pulled in tighter. So size increases as you go down and decreases as you go across. Now we're going to look at how does the parent atom, what we just talked about, the normal size of an atom compared to its ion size. So this is going to be the size of an atom when it gains or loses electrons, meaning when it becomes an ion. So you have to know what ion does every element form, and then how does that ion change the size of the atom. Okay, so we're going to look at the metals versus the nonmetals. So we've talked about how metals always lose electrons and they become positive cations. And nonmetals are going to gain electrons and become anions, negative ions. So what happens to their size if you lose electrons versus if you gain electrons? So metals, your cations, are going to become smaller because they're going to lose entire energy levels of electrons. And we're going to look at images of this. This is just the slide that you can write down, and then when we're looking at the images, you can process. Versus nonmetals, your anions are going to become bigger because when they gain electrons. So why is that? Opposites attract, okay? When you have the same number of protons pulling on electrons, okay, in a normal atom, right? When you have the same number of protons as electrons, because remember, all atoms are neutral, okay? But when you add more electrons, okay, when a nonmetal gains electrons, remember, you're adding electrons to that atom to fill that energy level. The nucleus can't pull on each electron as well, so the atom gets bigger. Plus, you're just adding more electrons without changing any number of protons. You're adding stuff to that atom. It should get bigger, okay? Because you're just adding electrons, and electrons are what make up the size of an atom. So you add more of those, it should get bigger. So let's look at a couple images here. So here's a sodium atom with 11 protons, 11 electrons, and it has that radius. But remember, sodium's in group 1, and so it's going to lose 1 electron, all right? And when it loses 1 electron, it still has its 11 protons, now it has 10 electrons. Well, it's going to become smaller because it lost an electron. The size is going to drop. It's going to drop a lot, actually, okay? Versus a chlorine atom, which has 17 protons, 17 electrons. When it gains an electron, and now it still has 17 protons, it has 18 electrons, it's going to get a lot bigger, okay? So let's look at a couple more images for this. So here are some metals, okay? So this is group 1, lithium, sodium, potassium, rubidium. And this is the lithium 1 positive ion, sodium, potassium ion, rubidium ion. And you can notice that every single one, from the parent atom to the ion that it forms, it gets smaller, okay? Beryllium, and this is group 2, beryllium, magnesium, calcium, strontium, the normal atoms versus their ions. And these are forming 2 positive ions, so they're losing 2 electrons. So notice how much the size decreases between the two. You're losing 2 electrons, and you still have all the same number of protons, so size is going to get a lot smaller. And then again, aluminum, gallium, and indium, they're becoming 3 positive ions, and so they're getting smaller. Versus, here's nitrogen in group 5. Okay, nitrogen, normal atom. Nitrogen has 5 valence electrons. It's going to gain 3 to fill that energy level. It's going to form a 3 negative ion. It's going to get a lot bigger because you're adding 3 electrons to it. These are some group 6 examples. Again, getting bigger because you're adding electrons. These all form anions. And again, group 7, fluorine, chlorine, bromine, iodine, getting larger. So your metals get smaller, your nonmetals get bigger. And we're going to look at the whole trend for the periodic table. So this is a great image that's going to showcase the trend. So size is still going to increase for all ions as you go from top to bottom because you still have more energy levels, okay? But the trend is going to differ between your cations and your anions. So as you go across the cations, your metals, the size is going to decrease from left to right, just like it did for normal size. However, when you get to the anions, when you jump from a metal to a nonmetal, the size is going to have a big jump because you're switching from the metal, which is losing electrons, to the nonmetal, gaining electrons if you look in just like the same row, okay? And so, like if you compare boron, which is right here, okay, to carbon if it forms an anion, or nitrogen, it's going to be a big increase. However, as you go across the anions, your nonmetals, that trend is still going to decrease. So you're going to see a size difference, like it's going to decrease across the cations, okay? And then when you hit the anions, you're going to see a big jump in the size, and then it's going to decrease across, all right? So across the periodic table, across a row, you can't just say one generic trend, because you've got cations versus anions, which do different things. You can say the same trend as you go down the periodic table, but not across, because as you transfer from cations to anions, it's a totally different type of ion. So like if you look at lithium to neon, the lithium ion versus the, from lithium to nitrogen, the lithium ion is tiny, the nitrogen ion is huge. Those elements are in the same row, the same period, but they vary a lot on their atomic size, their radius. So again, this is trying to compare just your main group elements, so group 1, 2, 13, 14, 15, 16, 17, and it doesn't have 18 on here because, remember, your noble gases aren't going to form ions. So this chart, you got your ionic radius, it's just showing ions here, and it's in picometers. It's got the charge and the relative size. So I want you to notice is that all your cations, so lithium, beryllium, boron, carbon, this one has carbon forming a cation, the size decreases. But then when you go from carbon to nitrogen, there's a big jump because you're going from a cation to an anion. But then within the anions, within your nonmetals, the size is going to decrease again. Okay? So if you need to pause this and look at this more carefully and find these elements on your periodic table, I'd recommend you do that to understand ion size comparison. All right. Our third trend is ionization energy. This trend is how much energy does it take to remove an electron from an atom. So we're going to look at how does that change as you go from top to bottom on the periodic table and from left to right. So as you go down the periodic table, the amount of energy needed to remove an electron is going to decrease. And this has everything to do with size, okay? How attracted are those electrons to the nucleus of an atom is going to dictate how much energy is needed. So as you make bigger atoms, it's easier to remove electrons because they aren't attracted, they aren't held as tightly to the nucleus. Okay, they don't have as strong a Coulombic attraction. There's electron shielding. Versus as you go across the periodic table, ionization energy is going to increase a lot. It's smaller. Okay, those electrons are held more tightly. There's a stronger Coulombic attraction as you go across, and it becomes harder to remove electrons. So ionization is going to decrease down, increase across. So here's a good image of that. Ionization energy is going to decrease down, and it's going to increase across. And that has to do with Coulombic attraction and nuclear charge. So as you go down, yes, there's of course more protons. However, those electrons are super far away. They're further and further away as you go down, and so those electrons don't feel the full pull of the nucleus because electrons on lower energy levels are shielding it. Versus when you go across the periodic table, remember the distance is the same, and so you are only changing the effective nuclear charge, which is increasing from left to right. And so the atoms with the highest ionization energy are going to be in the top right corner of your periodic table because they have the smallest size, and with the highest effective nuclear charge, those electrons are going to be held super tight, and it's going to be way more difficult to remove them. Because the tighter electrons are held, the harder they are to remove. Our last trend is going to be electronegativity. This is probably the one we'll come back to the most, this year. It's going to explain a lot of other things in the following units this fall, but it has to do with the tendency to pull an electron in a bond, or it's how the desire of an atom to gain an electron. How badly does an atom want to gain electrons? That's the more the desire, the higher the electronegativity. Okay, so this is kind of the opposite of ionization energy, kind of, because so how badly or how much energy does it take to remove an electron? This is how much does an atom want to gain electrons. Okay, so if you think about what kind of atoms already want to gain electrons, we want to think about those ions that want to form negative ions because they want to gain electrons to fill energy levels. So those nonmetals are going to have higher electronegativity if we're comparing them to the metals, okay? Because remember, think about what kind of atoms do you think don't want to gain electrons? Well, your metals. Your metals want to become cations. They want to lose electrons. So they're not going to have high electronegativity. Let's talk about why. So it all has to do with how large the nuclear charge is, the number of protons, compared to the distance electrons are from the nucleus. So it's those two concepts we've been talking about this whole time. So if we look at a sodium atom, it doesn't pull an electron. It wants to lose an electron, okay? It wants to lose its one valence electron. It's going to have a low electronegativity. Versus chlorine has 7 valence electrons, okay? It's a nonmetal. It wants to gain one. It really wants to pull, or it really wants to gain one electron. And what's going to happen, and we're going to study later here, is that these two atoms will form a bond called an ionic bond because sodium's going to lose one electron. It wants to get rid of it and give it to a chlorine atom which just wants one. They're going to transfer that electron. And so this has a high electronegativity, low electronegativity. And so if you like these images, okay, electronegativity is going to decrease as you go down the periodic table. It's going to increase as you go across. It's going to decrease as you go down because electrons are further and further away, so they don't feel very much pull. And these are your metals. Okay, so your metals don't even want to gain electrons. So elements with the lowest electronegativity are going to be in the bottom left, versus as you go across the periodic table, it's going to increase because electrons are being added to the same energy level, and as you get closer and closer to filling an energy level, it's going to increase, and the electronegativity is going to get higher. Now, here's a chart that shows the relative electronegativities of all the atoms on the periodic table, from hydrogen, lithium to fluorine. But I want you to notice your noble gases. They don't have electronegativity values. Remember, they have filled energy levels. Anything with filled energy levels doesn't want to gain electrons. So they don't want to form bonds, and so they don't have electronegativity values. Now, I hope you notice on your periodic table that electronegativity values are written. A lot of you have seen that before. Okay, and I want you to know that electronegativity value is a relative value. It's on a scale from 0 to 4, and fluorine is going to have the highest electronegativity value. So if you look on your periodic table, you'll notice that electronegativity of fluorine is 4.0 versus something like cesium, I believe, has 0.7 electronegativity, so a lot lower. So my question on this slide is, why is fluorine the most electronegative? Okay, we have to think about two things. One, the size of the atom versus the effective nuclear charge. So as you go down, the size gets bigger. Okay, and so even if we look at like fluorine, chlorine, bromine, iodine, astatine, these all have 7 valence electrons. They all want to gain one more to be like the nearest noble gas. Okay, fluorine wants to gain one to be like neon, chlorine, argon. Okay, but the size, the fluorine's the most electronegative because it has the smallest size, or the fewest energy levels, so the least amount of shielding, so those electrons are held tighter. And so it really, really wants to gain one more to fill that highest energy level. So let's kind of look down here in words so you can write that down. It has the highest effective nuclear charge, okay, with electrons being closest to the nucleus. So column 17, group 17, they all have an effective nuclear charge of 7, okay, with that 7, effectively 7 of their 8 valence electrons filled, okay? And so they all have the same nuclear charge. However, the distance is those electrons are closest to the nucleus in fluorine. And so there's the greatest desire to fill that energy level because those electrons are so close. I gave you this sheet, this summary of your periodic trends. It goes over all the information I just covered in this video, and it should be very useful to you. It has the atomic radius, ionization energy, electronegativity, difference in cations and anions. Please use this to help you review these trends or rewatch this video, the portions that you need, so that you can understand these trends and be successful in explaining them on the upcoming test.